All right. Hello, everyone, and welcome to The Current, the North Central Region Water Network Speed Networking webinar series. For those of you who are not familiar, my name is Ann Nardi, and I'll be the facilitator for today's session. The North Central Region Water Network is a 12-state extension-led collaboration working to increase interdisciplinary collaboration around water resource management. And we've been having this speed networking series for almost 10 years now, where each month we feature a different water-related topic and feature different presentations from experts doing research and programming surrounding that topic. So excited today to be featuring phosphorus management and water quality and have a great lineup of speakers ready for you. A couple Q&A or a couple logistical items for you. We will have a dedicated Q&A session for today's webinar. It will be after all three presentations. Please put your questions for our presenters in the Q&A box, which you can find at the bottom of your screen. It should have a Q&A with 2 word bubbles there. If you put, we also have the chat, which is available if you'd like to say hi to other folks on the call or for our presenters to share any links to their labs or work. But please put your questions for the presenters in the Q&A panel. That's how we'll ensure that we can answer them and get them addressed during the question portion of today's session. We will also have the upvote function available. So if you see a question that's really similar to one you have, please upvote that so that we will get to those questions at the end that are the most popular, the most upvoted first. If you are experiencing any technical issues with today's session, you can use your phone as your audio feature. You can do that by clicking the up arrow on the mute icon and then clicking switch to phone audio. Today's session is recorded, and we will post the recording for today's session as well as the PowerPoint slides for today's session on our website, northcentralwater.org. You can also go to our media archive on our website and find recordings of all the last webinars we've done over the last 10 years. All right, great. Let's go ahead and get started. We have a great lineup of speakers today that are going to be talking about phosphorus management. Gurbir Singh with the University of Missouri, Peter Tomlinson with Kansas State University, and Becca Munich with the University of Arkansas. So a great lineup of land grant researchers researching phosphorus management as it relates to agricultural conservation and field runoff, as well as modeling. So excited to feature all three of their work today. First up is Gurbir Singh, and I will not read his full bio here for you, but he is a state extension specialist and landscape management position at the University of Missouri, and it's going to be sharing some of his work in terms of the overview of agricultural conservation BMPs and their impact on phosphorus management, as well as some of his other work into specific BMPs and their impact on phosphorus. So I will stop sharing and hand it over to you, Gurbir.
Thank you, Anne. Is my screen shared properly?
No, oh, hold on, it's a little bit of a delay. Let's see. It looks great.
Okay, thank you. Thank you, everyone, for the webinar series, and thank you, Anne, for the introduction as well. So what I'll do is, in this presentation, I'll actually cover some background for the P cycle and the sol, and how different fractions and how different pools of P are correlated to each other, and then I'll move into the BMPs and some of the work that we are doing. So the most important thing that we need to understand is the P in sol is available in 3 major pools. One is the fixed pool of the P, second is the active pool, and then the third is the P, which is available in the sol solution. And if you see the right-hand side of my first slide, it actually gives the corn plants right there with the conventional till and no-till. And then in the center of it, I have the sol solution P. And the sol solution P is readily available for the plants to uptake. And that's what is the most important form of P that plants have to take up. There are several factors that actually influence the availability of P in soil. One of the most important factors is soil organic matter. And the availability of P from soil or organic matter is dependent upon mineralization and immobilization processes. Second most important factor for the P pool and soil is the clay content. Higher the clay content, the P is retained to the soil on the exchange sites better when you compare it to the sandy loam soils. Then we talk about soil minerals. If the soil itself have higher iron and aluminum content, there is the greater phosphorus adsorption capacity of those soils. And then the availability of P in soil is also highly dependent upon pH. It's mostly available at 6 to 7 pH, that is near neutral pH. And as the soils become more acidic, the iron aluminum comes in, and then there are strong bonds between the phosphates available in the soil solution, and then the adsorption of that P to the iron aluminum actually fixes that P into those bonds. Some of the other factors that actually regulate the P availability in soil are the temperature, moisture, soil aeration, and the organic matter decomposition as well. Um, Moving next, one of the facts that we all know about is the buildup of P in soil. So I took out a couple of the graphs from the published data. The first graph right here is from a 111-year long-term study, which is part of University of Missouri Ag Experiment Station, and it's a Sanborn field. And it's the third longest term trial running on crop rotations throughout the world. And if you see this graph right here in continuous corn, wherever we have added fertilizer, we actually had a built up of P over time. The second graph is one of the study that we published in 2016, in that we made Olsen P in the soil, and which is on the y-axis, and the years are on the x-axis. And if you see, we had three rates. One was the control, that is designated by P0, and then the second one is P13, and then the third one is P26. And as you see, as the number of years go on, we have more drawdown of P from the control. We dropped the Olsen P from 65 ppm to all the way to 35 ppm for PO. That is the third most line over here. And then the last graph in here suggests that P stratification. Most of the Midwest soils, when we are doing a lot of conservation tillage practices, specifically the no tillage, and then add more crops into the rotation, what we are doing is we are adding organic matter on the soil surface, and then we're adding fertilizer as well on the soil surface, and that ends up into more available P on the in the upper soil horizon, basically 0 to 6, 0 to 15 inches when we compared it to the deeper soil cores. So these are some of setting up the background that how we have added fertilizer historically into our ag systems, and it's available over there. And that's the source of the fertilizer, which eventually loses or it makes its ways into our headwater streams. The second thing that we have to talk is the legacy P, which is source versus sink. I got this conceptual model from one of the 2020 papers, and you see this, it illustrates how stream bank legacy sediments could act as either a source or sink for phosphorus at various fluvial positions. So essentially, if we have added a fertilizer historically 50 years back or 30 years back or 20 years back, that phosphorus is still there, and it's going to eventually make its way through the downslope going towards the bank of a creek, bank of a stream, which acts as a sink, temporary sink. And when the erosion happens, that P that has been bounded in some form of organic matter or some form of sediment, it stayed over there for some chronological time, and then it eventually become available through the microbial process or cycling, P cycling happening at that phase, and it eventually makes its way. So legacy P is a very important key. And if you see the graph right here, this 2023 paper, it shows the lag time in P release from the sediments eroded into the sediment into streams via bank erosion. So soluble P is readily available. And if you see the iron P, apatite P, and residual P, it takes a lot of time for those P to become available into our stream waters. So moving next, some of the factors that we have to consider, or BMPs we have to focus on for managing P practices to reduce P loss. We actually categorize them based on source, transport, and sink. Source is one of the major aspect that my research has been focused on, and how we can manage it in field is we can have balanced P inputs based on the soil test P and yield. We can do a proper management of fertilizer application. It can be deep banding, but there is a practical aspect to it. P application timing is very critical. We have looked into on our several of our studies that we have done over here. P rate is going to be one of the most important factor as well. When we contract out our fertilizer application to co-op, those spreaders need to be calibrated well enough so that we put the right rate on it. Tillage is an important factor as a source because sometimes the tillage actually helps in mixing up the P in the soil. But when we have slope, we do not have an option of tillage, then that management practice can result in a P stratification. Then we talk about soil health, cover crops, crop residue management, that also adds to the source. And then there are animal manure sources that add more complexity to the sources. Then we talk about the transport. Transport of P is we can minimize the erosion and runoff and leaching. We can reduce the connectivity to the stream. We can implement some practices like land leveling, terraces, wasp cobs. We can use cover crops to minimize the transport, as well as we can use grass filter strips. We can manage the transport through two-stage ditches. We can use bioreactors. We can use saturated buffers. And finally, the last aspect of P is the sink, where the P ends up. We can have a better management in form of developing drainage water recycling systems, which are the part of on-farm practices. So we can increase the residence time of P in the tailwater ponds. We can develop we can have constructed wetland to manage P. So overall, if you see, this actually lays out the source, transport, and sink for P. My research actually have looked into all these the highlighted points right here, number 3, number 5, number 6. We have evaluated 4, 6, 8, and 9 under transport, and we are evaluating the sinks as well into my research. So I'll shift gears quickly towards some of the research that we have already published. So this is one of the projects that we started in 2016, and we started looking into the paired watersheds, which are 6 paired watersheds in this study. What we did was we had 3 watersheds. We actually had planted cover crops, and we had 3 which we did not plant it in cover crop. And then we monitored the water quality from these watersheds for. We're still monitoring. For this publication, we published in 2020, and we laid out the background data for it. And if you see my graph right here, and the circle I highlighted is the total P. we didn't see any differences, the significant differences in reduction with total P with and without cover crops. The total P was lower, but the reductions were not significant. Second research that we did and published was tillage and cover crop interaction. Our objective was to evaluate the impact of cover crops and corn soybean rotation under conventional till and no-till systems on leaching of dissolved reactive phosphorus measured through lysimeters installed at 30 to 40 centimeters and 100 centimeter depths. And the graph right here, if you see the circles, essentially, the x-axis is the timeline and the y-axis is dissolved reactive phosphorus. And circles, you see, whenever we put out P fertilizer, on these agriculture fields, we do see a peak of DRP. We do see a peak of DRP in 2016, 2017, and we did see the same thing in 2017 and 2018. So once we add that fertilizer, the source is available, and then it's the precipitation amount, the amount of rainfall that we are going to receive in next coming days or in coming month. That's going to drive the amount of P that will lose into our headwater streams. This is another project that we published, and in this project, our aim was to compare the effectiveness of winter cover crops in reducing runoff, total suspended solids, nitrogen, phosphorus concentration, and ephemeral streams in non-tile drain headwater agriculture watersheds. So in this map, you see the green outline is for our watershed where we had the cover crops, and black outline is for the watershed where we did not have any cover crops. And we compared both of these watersheds for the water quality at the yellow points where we had the ISCO and the flumes for monitoring the water quality. Some of the results, if you see with the cover crops, these are the hydrographs. And for both of these graphs right here, the first graph on the left-hand side, you see the green line is for our cover crop treatments, and our discharge was lowered with our cover crops when we compare it to no cover crop watersheds. On the right-hand side, if you see the graphs, and if you see the top graph is for the discharge. Any value which is negative, it means the cover crop watershed lowered the discharge compared to the no cover crop watershed. Interestingly, if you see my lowest graph right here with the red circle, the cover crop watershed actually resulted in increased DRP concentrations into our streams. And that is because this is a no-till watershed, and both of these watersheds were no-till. And then with 8 years of monitoring, what happened is we actually added, we stratified that P on the top soil surface, which actually resulted in more dissolved reactive phosphorus losses into our headwater streams. So this gave us an idea that why not we should look into stacked best management practices. So the stacked best management practices is just going to work like a home water filtration system where we have stage 1 filtration, we have stage 2 filtration, we have stage 3 filtration. So this concept we published out in 2020 in a review article that if we have to manage P, we have to tackle it from all angles. We cannot do just one management practice and say that we can manage P. It's going to be very, very tough. So you see how I laid out the stage filtration system. Phase 1 is going to be in field where we do 4R nutrient management practices. Stage 2, and we can add cover crops in that scenario as well. Stage 2 is going to be where we have wasp cobs or terraces or structures which actually limit the outflow of the water. Basically, the water quantity is managed over there. And the stage 3 is going to be once that water leaves our system, it ends up into our saturated buffers, riparian buffers. We can come up with some of the structures where we can tackle that as well. So to test out this hypothesis, what we did was we established this study in 2018. And the overall goal of the study was to determine if the stacked practices of drainage water management, wood chip bioreactor, and saturated riparian buffer can reduce annual total discharge, total suspended solids, total N, nitrate N, total P, and DRP. And in this map right here, you can see that we had tile drainage system. And then we had the drainage water management, basically the control structures for managing the tile water. And then we had a bioreactor, which is provided in the green color right there. And then we had the dashed green line was our saturated buffer line. So basically, it was a stacked best management practice. So moving into the results from this study was ran for 5 years. And if you really see for the total P, we did saw a reduction in total P with the stacked practice, but this was not again significant. The ortho P is actually the DRP. We did not saw any significant reduction with the stacked practice as well. And this graph is the cumulative total phosphorus over 5 years of the study from the stacked practice. And if you see the red line is the influent coming from the system, and we had total 10.4 kg per hectare of total P incoming. And the blue line is the line which is connected to a stream, and that's the water that leaves our system. So we did reduce the total phosphorus load, but it was not significant in this case. So next, what we are doing is at this point is our ag experiment station at Grace Greenlee Research Farm. It has been converted into conservation showcase, where we were able to get a 13-acre lake on our ag experiment station, and we are doing drainage water recycling research in-house at this research station. And if you see this picture right here, you can see the algal bloom on the sides, on the edges of this lake. And this lake has, next slide, I'll show you how much area it has. But if you really see the blue points on this, blue points are the monitoring sites where we are monitoring the inflow of the water, and the golden point, golden star, is the star where the water is leaving this lake. And this map actually shows the watershed contribution into this lake. And essentially, we are doing calculating load based on output and input. And this video right here shows the installation of a flume that we installed in 2020. And we have been monitoring this lake for a year and a half for the loads coming in and going out. And the outlet pipe.
Kabir, sorry to interrupt. We're running tight on time. Just wanted to give you a
Okay, I'm gonna just wrap up in a minute. Thank you. And if you see this this outlet pipe right here, we haven't seen any flow from this outlet pipe for almost a year. So drainage water recycling on farm can actually really help us in reducing those P loads. As long as I can manage all the nutrients on farm and I can retain them on my farm, then I don't have to worry about the P going into our headwater streams. To wrap up this, take-home message is going to be managing P loss from agriculture field is complex. Legacy P needs to be evaluated for its role as a source or a sink in agriculture fields, riparian buffer areas, and stream banks. A suite of BMPs as stacked practice might need to be implemented to reduce P loss through agriculture fields. Managing runoff water will be the key to reducing P loading into headwater streams, which can be achieved using an on-farm drainage water recycling system. And I'm very thankful, and I would like to acknowledge all the sponsors that have actually helped us in funding and carrying out this research. And I have my email over here, and I'll be available for the questions. Thank you.
Thank you so much, Kabir, and thank you for overviewing a lot of different research there, which is great. I see some questions coming in. All right. So next up, we have Peter Tomlinson, and he's going to really be talking about similar work that he's doing at Kansas State with collaborators looking at transport. Peter is an associate professor and swing extension specialist with the Kansas State University. He's also a key collaborator with the network on the North Central Climate Collaborative. So we're excited to have him here today, sharing a little bit of his work as it comes to phosphorus runoff. I'll stop sharing and hand it off to you, Peter.
Thank you, Anne. Here we All right. Is that showing correctly?
Looks great.
Okay. Well, good afternoon, everybody. We'll jump right into phosphorus, and particularly thinking about how does no-till management, cover crops, and phosphorus management interact. And so, Kansas State University, a group of us got together about 10 years ago now, and the question was, we were getting a lot of questions about, what sort of reduction values do we put on a best management practice such as cover crops for reducing phosphorus. And so we had done a literature review, and there really wasn't any data at that time to say, one way or the other. And so that was really what led us to start the Kansas Agricultural Watershed Project. And the faculty team listed here has pretty much been intact since the beginning. We've had a couple retirements and a couple new additions, but generally we've been all working together on this project. And you can see we've had a number of graduate students that have finished their degrees, and numerous undergrads and interns that have made all of this work possible. So, the real questions that we wanted to get at here were, how will cover crops and pea fertilizer management affect sediment and pea loss in a no-till production system? And so, will cover crops affect, as we think about the 4 R's of nutrient management, the right place and timing of pea fertilizer? And so from that standpoint, the first 5 years of this project, we focused on the cover crop question. We focused on fall broadcast versus spring placement, all under a build and maintain recommendation model. And so, and then, as we think about we've got the cover crop piece, and then we think about the placement and timing. We can then look at, all the economics of planting the cover crops, the, cost of applying the fertilizer by these different best management approaches. And then we can look at economics. I'm not going to get into that today, but we've got a number of publications out from the first cycle of this work. And so this is just an overview of our Kansas agricultural watershed. We've got a total of 18 watersheds set up. They all have ISCO automated samplers for collecting surface runoff. And the site is about a 5 to 6% slope. And all of those terraces, the red arrows note the direction of drainage. So we did do some dirt work in 2015 at this project to make sure that everything was sloped towards our collection equipment. We installed all of the flumes, and because of that, the very first year, 2015, this field had been conventionally tilled, and so we did one final tillage activity to remove any compaction from the construction equipment. And so we say we started in 2015, but really our first true year of no-till was 2016. And so the first phase ran through 2019, as I've already indicated, was a build and maintain management approach. And so that resulted in fall broadcast of 56 pounds of P2O5, and then a spring 2x2 placement at planting of 56 pounds of P2O5 per acre, both the corn and the soybean years. And so our treatments are, from a cover crop standpoint, are either no cover crops or winter cover crop, and you can see listed there. We've generally always had we have always had a cereal. That has been the constant. It's been triticale, it's been wheat, it's been cereal rye. And then we've experimented with having rapeseed or hairy vetch in there. The reality of what we see planting after, particularly after corn, but also after soybeans, we don't have a great window to get the brassicas to establish, and we've seen, just some really small plants in the fall and then nothing in the spring. And so then in 2020, we made some management changes. We entered a new funding cycle. We had seen what that fall broadcast versus spring injected was doing for our runoff values. And so as a group, we came together and said, what if we take that fall broadcast, which we know is not an ideal practice, and we convert that to a sufficiency-based management with spring applied P in a 2x2 placement. And then what if we, continue that, what was the spring injected treatment, we continue that as a spring injected treatment under a build and maintain management philosophy. And so that's what we have been looking at since 2020. We kept the cover crops, been a bit more consistent since 2020 with cereal rye as our cover crop. And, one of the things, so we'll jump into the data now, and one of the things that we were shocked at how quick we were able to document was the development of stratification in our watersheds. We had come out of a conventionally tilled field, in the top 2 inches, we were about a little over 30 parts per million, malic 3 phosphorus. And, just in the course of those first 5 years, we jumped to around 70 parts per million in the top 2 inches. We've actually done some additional work and looked at just the top inch, and it goes well over 80 parts per million in just that top inch. So, as we think long term about phosphorus management, we really do need to think about this P stratification in no-till production systems and what those implications are from a water quality standpoint. One of the other questions that we've been able to dive into a little bit with this project, frequently, I've heard producers say, I don't think I get as much runoff, where I've got cover crops. And what we've been able to document here is, and this is just looking at the annual runoff volume, is that, there's been a handful of cases where we've seen a reduction in runoff volume, 2 out of the 7 years presented there. But really what we've seen when we look at the hydrographs is we're changing the intensity of that runoff event. So rather than it seeing a rapid spike in discharge, we see a lower peak flow and a longer flow duration in our watersheds with cover crops compared to our watersheds without cover crops. And I think that has a couple important implications for some of the other findings that we're seeing. The first one, is when we look at the soil loss, or the amount of sediment that's being lost through erosion. Our cover crops have done a phenomenal job reducing that erosion loss above and beyond our no-till production system. And so we consistently document a 60 to 70% reduction in erosion. And so I think that is a real win for cover crops. And we'd think if we're seeing those sorts of reductions in erosion, well, we'd think we should see some reductions in total P. This is where the story gets a bit muddier. When look there through 2016 through 18, 2016, 17, no difference in total P loss. 2018, we actually saw more P loss with the cover crop. And then in 2019, we saw a reduction in total P loss with the addition of cover crop. Part of that has to do with the characteristics of the storms that happened that year. When we see that similar trend in 2020 as well. And we thought, maybe there's something really changing in the system. But then when we got into 2021, no statistical difference in total P loss. And in 22, we actually saw greater total P loss with the cover crop. And so, total P is I think about it as kind of the black box measurement. There's a lot of nuances in terms of our P pools. And I think an important one that we need to think about is dissolved reactive phosphorus. And what we have seen is consistently in 6 of the 7 years, we've seen an increase in dissolved reactive phosphorus where we've in those watersheds with cover crops. And this is across, all of the P management. I think part of what is happening, and I think it ties back to that nutrient stratification, is that we've got an enriched near surface soil that has a lot of readily available phosphorus. The cover crops are also slowing down the runoff flow and extending that runoff duration. And so we've got more residence time of that water interacting with that near surface soil. And it's our hypothesis that is what those two factors come together in part to why we're seeing this higher dissolved reactive phosphorus. So if we're seeing higher dissolved reactive phosphorus, we're not necessarily seeing consistently, higher total P. Well, what's changing? Well, and we think this ties with the reductions that we see with cover crops and the sediment, is that we're reducing our particulate P loss with the cover crops. But when we look at it, from a full picture, when we think about that runoff water, being delivered, downstream, that dissolved reactive phosphorus pool is an important readily available phosphorus pool that we need to think about how we adjust our management for that. And so we'll switch over here and look at some of the fertilizer, the fall broadcast for spring injected. what we've observed here from a dissolved reactive phosphorus standpoint is, we see higher dissolved reactive phosphorus in the fall broadcast. Tend to see lower dissolved reactive P with the spring injected, and then those are our control that hasn't received any phosphorus is the lowest. And that pattern tends to hold for our total P as well. And we've got those highlights there at the top. We've seen anywhere from 5 to 50% decrease in dissolved reactive P loss using spring injected, and somewhere between 1 year no difference to up to 34% decrease in total P loss using spring injected. And so, that was, with that fall broadcast versus spring injected. Now we're going to jump into the most recent data coming off of this project. And so we maintained our control. The sufficiency treatment actually has been in a drawdown phase because that had been in the first 5 years managed under build and maintain. We managed it under a drawdown approach. And so no phosphorus was added to the system in 2020 through 2022. And then we've been applying a maintenance rate in the what's represented in the blue bars, the build and maintain. So as we look at this, we've got some more interactions here, but we have documented about a 19% decrease in total P for that sufficiency management during this drawdown period without the cover crops. About a 45% decrease in total P for sufficiency management with the cover crops.
Hey, Peter, sorry to interrupt. We're getting a little close on time.
Okay, I've just got 1 or 2 slides and I'll wrap up here.
Great.
And so, when we look at the dissolved reactive P, we see very similar trends there with that sufficiency drawdown phase, 29% decrease without cover crops and 46% decrease with cover crops. So I think this highlights that we do have the potential to, with smart phosphorus management, to make some impacts on phosphorus loss. And I think this gives us some insight and things to think about as we look to the future of phosphorus management. So with that, I will end there, and all of this work would not be possible without the multiple funding sources recognized on this slide.
Thank you so much, Peter. And I really appreciate that research, both from Peter and Gerbir, showing, that relationship between cover crops or other ag BMPs and phosphorus runoff is not always linear in that way. So looking peek behind the curtain at some of the complexities here. Next, we're going to move to Becca Munich, who is with the University of Arkansas. And Becca's going to be talking a little bit about some of her work when it comes to P transport modeling. So thank you so much for joining us here today, Becca.
Okay. Hopefully you can see my screen okay.
Looks great.
Great. Thank you for having me, and I will do my best to stay on time here. I'm going to switch gears a little bit from the 2 previous speakers and talk more broadly systems-wide thinking about phosphorus modeling and sustainability and management. So I will just say, to the cover crop story, because I saw lots of great questions in there, that the kind of data that we now have from groups like these 2 previous speakers, we were seeing very similar things on the modeling side before we had a lot of data to back it up. So I'll just put that in there, that those complexities can sometimes be captured in models before we have the data. Before I start, I'd just like to acknowledge that my scholars do, all of this work, both current and previous students and postdocs. I just want to thank them for all their hard work. And I'll just throw this up here briefly. I gave my slides to Anne and team so that you guys can look at this later, but this is only a small facet of what my group does. So if you want to learn more, there's the info. It's in the slides that'll be sent out. And I always like to start with where I'm going because this is kind of a learning approach and something I use with my students. Here's what I hope you get out of my talk, that we need more data, especially when it comes to things related to water quality like phosphorus. We can't discount the importance of knowing more about the inputs going into these systems. We have to think about how machine learning and maybe AI plays a role in all of this. And but despite using these new methods, we shouldn't give up on our traditional approaches. So I just like to start with a few kind of key points that environmental and water systems are very complex, and interactions within the system are often nonlinear. And so thanks, Anne, for kind of summarizing the previous talks, because those nonlinear things are really important when we're trying to understand at a larger scale too. We throw people into the mix, like this is my grandfather and dad in a river in Arkansas, who knows how long ago. We just elevate the complexity of the system. So we're already working with these really complex systems with people influencing them in many different ways. So, one of my driving questions is, do we really have enough data to improve the way that we manage these systems, especially for water quality? So I'm picking on Wisconsin here because I gave a talk at Marquette and I already had this data pulled, but I could do this for any state in the Midwest or really in the US. If you start to look at some of the water quality data available in Wisconsin, I just went to this one site. There might be more out there, but from this one site, there were over 24,000 monitoring sites. Nutrients included about almost 9,500 sites with over 800,000 sample results. So everyone's reaction is one of two things when they see these numbers, and maybe look at this map where you can kind of see the points to the right. Everyone thinks either, wow, that's a lot of data, 800,000, that's close to 1 million, that's a lot, or wow, that's not a lot of data. And so if you take those nutrient sites specifically, which would include phosphorus, and you divide how many observations we have by how many sites that there are, that's about 90 results per site. And then if you divide that even further to like number of years, assuming you have one sample per month, it's about 7.5 years per site, which is quite good. But that's assuming you only have one constituent. Maybe you're just measuring total phosphorus or just dissolved phosphorus. So if you're thinking about what all water quality is made up of so many constituents, and if that's all the data we have, maybe we don't have that much data. So back before I was born, I'm not going to say how much longer before I was born, there's a famous quote by Ward in 1986 that in water quality, we are often data rich, but information poor. So we have a lot of data, but we're talking about systems that are constantly in flux. And this famous quote, which I updated to be a little more modern, that no human ever steps in the same river twice, where it's not the same river and they're not the same human. And this is definitely the case when we're talking about these systems that are constantly changing over time. So in the US, we see similar details on how often things are monitored. So this study out of Duke showed that only about 20% of watersheds in the US have one monitoring observation in the last 2 years. You can see it's concentrated in a few key places, but there's a lot of the US that's currently unmonitored. You kind of zoom in, you can go to that link when you have the slides and zoom in where you are. You can kind of see where things are monitored and where they're not, and a lot of other interesting data. So, what could we be missing when we are kind of, in my opinion, under monitoring at a large scale? We miss important events, even if we're, measuring with some sort of flow rate triggered sampler. And model improvement by increasing observational data is kind of lacking, and then understanding over time or space under different situations, right? And then for fun, I always like to include some like strange things that happen in the environment that we definitely aren't modeling for. So if you want to check out my website for a little bit of fun, feel free to do that. So in my humble opinion, we don't have enough data across our water systems, especially for water quality, given the complexity. So that's poop. If you thought that was really nice, pretty pond, it's actually poop. And we can talk more about that later too. So I hope I convinced you maybe a little bit that we need more data, that we maybe don't have big data in water quality like we like to think. So I'm not going to just talk about problems. What are some solutions from a modeling perspective? One, let's create new data. Where we don't have data, figure out ways to create new data. Embrace new methods, as I already alluded to, and improve those models that we already have, because they kind of help bridge the gap when we don't have a lot of data. So I'm going to talk very briefly about each of these, and hopefully leave more time for questions and discussion. So the first, paradigm challenge I have for modelers like me and just people who work with models is that average inputs or static inputs, one data point over, many years over the same year is just not going to cut it. We need to have a better system level understanding. We need data that is dynamic and, observed as our systems change. So you may or may not know that 50% of all phosphorus inputs into the landscape come from manures. I was gonna, see who might know what kind of data we have on that, but for time, I'll just skip and say the biggest data source we have is the USDA's census, animal agriculture census, and we have one data point per animal type per county across the U.S. every 5 years. And that's the most consistent and comprehensive data we have, and it's a great asset. But if you think about animals that move across the country, from going from a capping operation to finishing, or we have chickens and poultry, some livestock that have a rapid turnover rate, are we really capturing what we need to in this important source? So we can manually start to think about where are the animals by just looking at some images like a couple of NGOs have been doing to map feeding operations specifically, because that's where a lot of our livestock are. We can comb through records like we did in this paper to try and get some of that data where we don't have it. Or we could embrace some new methods, remote sensing and machine learning, like we're doing in a project funded by the STEP Center, which I'll talk about later, and try to identify them using remotely sensed data. We can also, in this bottom right, we use remote sensing to look at where manure is actually being applied to fields, not just the barn. So we're essentially creating new data to fill in that gap where we have an important input gap that could be affecting how we model and understand these systems. So that's just one brief example for time. We can't discount the importance of getting those inputs right. And that also includes farmer management data, which we rarely have access to. So next, I want to talk about new methods. So we have to embrace machine learning and even AI. That doesn't mean we aren't going to give up our other models, but we definitely need to be thinking about how to use them. In that last slide showed one example, but I'll just say, we can't ignore the AI approaches because they might be black box. I think there's definitely a lot of creative ways that are now out there to incorporate these kinds of methods into our existing methods and to apply to our existing data. I was doing this back in my undergraduate program, and I was told because it was a black box that maybe I should try something different. So I just want to point that out there that we've come full circle here. So we're working on integrating machine learning and AI into our work by simulating hydrologic systems. This is an example of some work where we're applying graph neural networks to water quality prediction. This takes into account the spatial connectivity of water quality when we're trying to understand the system. So it's a pretty cool and new approach. We're using a new technique developed by some of our computer science colleagues in terms of causal learning to inform how our models are developed and how to refine the parameters and parameter space that we're using. These are just two examples from our group. There's a great paper, which I included in here, since you'll have the slides if you want to read more and get kind of an introductory primer to how we can use machine learning in this context. I left that in there for you, but we're definitely going to have to start using machine learning more and at various scales. And then finally, we really need to improve those process-based models. Just because our models are good enough doesn't mean there's not room for improvement. And again, they're a key point to kind of bridge that gap where we don't have a lot of data or we have to wait years to get the data, right? So we're working on this in a variety of contexts. I'm just going to throw them all up here so thinking about how we can use some of the data we have or create to improve these models and integrate more data, more precise details into our modeling systems so that we can better bridge that gap. And then with my last little bit, recapping our work, again, these relationships, environment, water, nonlinear, complex, we have a lot of data, but it's not enough. We need to think creatively about how to get more information to make those key management decisions at a larger level. So hopefully that I've convinced you that I got to those thoughts. And then with my last little bit, I just want to mention that we do have a NSF funded Center for Science and Technologies for Phosphorus Sustainability that is working with people from the material scale to the global scale, researchers, integrating stakeholders, especially with the help of the Sustainable Phosphorus Alliance. We have a roadmap for phosphorus sustainability, and some of the work I presented here is funded by this center. But it's a great way to integrate with researchers, if you are a stakeholder or if you are a researcher, to get integrated with other portions of the whole phosphorus chain, and try and develop technologies and solutions that help us reach a 25% reduction in mined phosphates that we have as our vision. And then we're doing some steps to improve these models that I kind of mentioned. So really linking sources to some of that output data in terms of understanding what are the main drivers of P losses across the US, integrating isotopic tracing, which is fairly new in terms of tracing the oxygen it's bound to phosphate to look at what are the major sources. And then I'm going to leave you with that because I wanted to catch us up a little bit on time. Sorry, I set my own timer there. So if you have any questions, I'd be happy to answer them, but I did provide my slides if you want to dive in more deeply.
Thank you so much, Becca. I really appreciate that. And thanks to all of our speakers here. I know we have a ton of questions. This is certainly a topic that is on a lot of our minds when it comes to working with landowners and working with agricultural producers. I've seen one question kind of come to the top here. And so with our limited time, I want to make sure we at least have time to ask this. It's come from anonymous, but it's been upvoted a few times, and they're asking if you can elaborate on how cover crops could act as a source of P, which I think is, maybe one of those questions that as we take a deeper look can be a thought that we keep kind of seeing within the data. Is it true that it's a source of P, and how so? I'll direct that to all three of you, though I know that might be a little bit more for Peter and Gerbier.
I can jump in and give my thoughts. I think the cover crop does play a role. And I mean, we're adding another plant growing in the field that has a root system pulling phosphorus out of the soil, and it's additional residue that's being deposited on the soil surface. So I think it does play a role, but I think the more important role is, when we couple no-till and cover crops together, it's some of those changes in the runoff water interactions at the near surface that I think are probably the bigger player there. And, even without the cover crops, we have phosphorus stratification in our no-till systems that we need to be thinking about.
I would just like to add to it. I concur with Peter on that. We need to be thinking that if we try to phytoremediate a site or a mining site with a crop which actually mines the nutrients, heavy metals out of the soil, it's actually putting it into its biomass. So cover crops is actually behaving in the same way, where we have our bank reserve in our soil profile, where it's taking up the P into its biomass, and now we're putting it on the surface. And if it's a no-till system, we're actually stratifying more on the surface. So there is something that's happening in that P cycling, which makes that DRP or phosphorus more available on the surface. And at the end, it's going to be dependent on the rainfall and precipitation that we received. That's going to be the transport factor in that.
Great, thanks. We might not have any more time for questions. I'm sorry, I'm looking at the clock. I was trying to fit one more in and I don't think we can do it. So I apologize about that. That said, I know while we didn't have as much time for questions, it's because we had really great presentations. So I really appreciate each of you sharing your expertise. As Becca kind of alluded to, we will have the presentation slides and I will make those available. So there's lots of citations in there. I know some of the questions were in regard to citations or in regard to the references that they were noting. So I want to make sure that you go to our website at northcentralwater.org for a recording of today's talk, as well as those slides. I'll make sure they get up there probably in roughly 24 hours or so. I also want to put up this slide here today that has each of our presenters' emails. So we do call this speed networking because it is, you know, firing fast in terms of what is some of the research that's happening in the region. So hopefully that gave you a feel for some of it, and you can certainly reach out for more information as well as look at those slides for additional detail. I hope you can join us next time. May 8th is going to be our next edition of the current webinar. We always rotate different water-related topics. So in May, we're going to be turning to agroforestry and timber management. So taking a hard right turn there. I hope you all can join us then and have a great rest of your day. Thank you again to our speakers today.